Alright, to begin with, let's see how to launch Persalys from the SALOME environment using Singularity. You can do this through the graphical interface or, like in our case, directly from the command line. Two is to make sure that Singularity is actually installed on your system. This is one way to do it.
The second command is used to generate the Salome launcher. To do that, we run the Singularity command with 4 arguments that are run --app, install, and finally the Salome Mecha SIF image. You can download that image directly from the Cadastre website. This is actually a one-off command that creates a small executable launcher. It simplifies how you interact with the container. From now on, to launch Salome Mecha, all you need to do is to run this file right here.
Let's go ahead and use it to open SALOME in shell mode. From here, I try to run Persalys, but it actually fails with some glibc version errors. My system is too old for the required GPU libraries. That happens on your side, no problem. Just actually exit this Singularity container, go back to our command and add the soft option, --soft here. This actually switches to software rendering and avoids GPU related issues. Now I try to run Persalys and this time there should be no. So here is the main interface of Persalys. Click on New Study and it actually displays all the available models. At this point, we are interested with Kotlin model, as it actually handles the use of external softwares and codes such as Salome and Cadastre, as we have seen in the previous videos. Click here, and it actually gives you an overview of all the possibilities. In our case, we would like to begin by creating a design of experiment, evaluate it, and from that point, be able to create a meta model that will be later exported and then used in the optimal. So let's go ahead and define it. First command will be the one that creates the mesh for us. So we are going to use Salome in text mode without launching the graphical interface, and then we are going to use the Python script that we saw earlier.
Now that we have defined the command, the next step is to locate the template file that Persalys will use to replace placeholders with the correct variable values. We'll rename the output file as needed, and then we'll define all the variables from the template, setting their placeholders and their nominal values. This is actually a one-off command. I'm going to locate the output file name, and then we are going to indicate to Persalys where to find the exact value of the mass here as an output, which will be on the third row of the file. And that's it for the first command. The second command is about the computation step done with Cadastre. We will need to locate the Aster's export file runner, and then we define the export file to execute. In this case, the export file will not be modified by Persalys, as it only points out to the mesh file and the command file to be executed. And those two files will always keep the same names, because with each iteration, Persalys will just replace the old files with the new ones, keeping those names consistent each time. At this point, we are going to do the same thing with variables as earlier, that is to define them, define their placeholders and their nominal values. The resource here will be the export file. Once again, we are going to locate the output file and then define the line where the variable will be fetched by Persalys. In this case, it is the von Mises stress value. Finally, the third command is about memory management, as we want to delete the mesh after each iteration. Now we're ready to set up the probabilistic model. I'm going to select all these variables and assign a uniform distribution to each one. A uniform distribution is basically the default choice when you don't have more specific information about how the variables are distributed. We will also define the lower and upper bounds for each variable. From this point, we can now go ahead and create our design of experiments. We will go with the probabilistic design, choose the LHS by default method, and set our sample size to 100. Now that we are all set up, let's go ahead and evaluate our model. So we get to choose the outputs that are, in our case, the von Mises stress and the mass. Click on Finish and then Run. So what this will do is vary the defined variables for each iteration. Since we've set up a design of experiments with 100 samples, it will run through the process 100 times, following the chain of the 3 commands that we defined earlier. So we just monitor the progress and wait for all the runs to complete. So this is the results summary. Here we can display a table with all variables. We can also see a parallel coordinates plot, which is a great way to visualize how different variables interact across multiple runs. Now that the design of experiments is completed, we are able to build the meta model. On this window, the outputs are already selected and we get to choose the construction method, which is the Kriging here. We choose the generalized exponential and put the p parameter to 2. And the last thing we want Persalys to do is to split data into training and test samples. We click on Run and Persalys will evaluate the Kriging model with the defined parameters. So here are the results, and for the sake of the validation, we can use the curve fitting of the analytical values for both mass and von Mises stress values. You can see that right now our validation criterion is around 0.5, which is not really satisfactory. We need a better value to improve the model's accuracy. To do that, let's modify the Kriging model. So by default, the leave one out option is on, which sometimes leads to a less accurate Q-squared because it can overfit to individual data points. By turning it off, we avoid that overfitting and end up with a more generalizable and robust model. Now, once again, let's check the validation criteria for both mass and von Mises. So this is for the mass. And you can see that for von Mises, we went from 0.5 to 0.7, which is a better value. Now that the meta model is created, we can export it as a physical model for it to be used within the optimization process. When you open the optimization window, you will see a list of all the input variables. You can choose to optimize all of them or just a few, depending on your objective. A key point here is the starting point. A good initial guess can really improve the optimization's performance. A useful habit is to go back to the design of experiments results and look for the sample with the best performance. In our case, we want the one with the lowest mass that still keeps the von Mises stress below the limit, which is 1.5 times 10 to the power of 8 pascals. We scan the results, find that sample, and then manually copy its input values to use as the starting point for the optimization. Next, we define the constraint, which is the von Mises stress threshold, and enter the corresponding value. Then we choose the optimization method. Persalys offers several options here. If you're unsure which one to use, just click the help icon next to each method. That will open up documentation with a short description and the available parameters. Finally, we confirm that this is a minimization problem since we're aiming to reduce the mass. You can tweak other settings like bounds or tolerances manually, but we keep the default values for now. Once everything is configured, click Run, and Persalys will start the optimization process. You'll see a summary of your setup, including the method used, constraint value, starting point, and variable bounds. And here we have the result of the optimization. What you see here are the optimized values of the variables. These are the ones that led to a reduced mass while still respecting the stress constraint. So with this configuration, we have achieved a lighter design. This brings us down to the end of the video. I hope it was insightful. See you in the next one.